Welcome, everyone. I'm David Bader, and I'm a distinguished professor at the New Jersey Institute of Technology, and I also direct the Institute for Data Science. We're very pleased to have a distinguished speaker here today with us, Dr. Laura Haas. Dr. Haas is the Dean of the Manning College of Information and Computer Sciences at the University of Massachusetts Amherst. She was formerly an IBM Fellow and founder and director of IBM Research's Accelerated Discovery Lab. She's held a broad range of positions at IBM in both research and development divisions, and is best known for her work on systems and tools for integrating data that may originate in very different systems, be represented in diverse formats, and be of a variety of types. Dr. Haas has received the Anita Borg Institute Technical Leadership Award, the ACM Sigma COD Innovation Award, and several IBM awards, including a corporate award for information integration technology. She served as the vice president of the VLDB Endowment Board of Trustees and as vice chair of the Computing Research Association's board. She currently chairs the National Academy's Computer Science and Telecommunications Board. She's an ACM Fellow, a member of the National Academy of Engineering, and also a Fellow of the American Academy of Arts and Sciences. Today, we're very pleased to have her speak on data science for the common good.
What I thought I'd talk about today is is data science for the common good, a theme that's near and dear to my heart, and we're fortunate. We're in a really good time for data science, as you all know. Never has data been more available. Never has there been as much compute resource. Never has there been as much interest in what computing and data science can do for the world. And that leads to, well, I'm almost right. Okay. We don't seem to quite have, there we go. Sorry. That leads to wonderful headlines like, we're saving lives, we are helping children learn, we're helping farmers with their farming, we're helping elders feel less lonely, we're able to stop crime and prevent road accidents. All of these wonderful examples that can make us feel really good about these systems that we are working with. However, as you may know, bad things do happen, and so for each of those, you can pretty much find an equal and very pertinent negative headline. So we're causing accidents. We're making people more lonely. We are taking away farmers' jobs. We are damaging our children's brains, sending innocent people to prison, and heck, we're even killing people if you believe everything you read in the paper. Some of these are funny. Some of these are actually very much true and a failure of data science in some of these cases. And the thing that I think we all worry about is, well, what if public opinion and fear override some of the common sense value of these technologies we're looking at? We don't want to get regulated in unhappy ways. We don't want prohibitions on data science or certain kinds of technology or certain applications of it. We want, in fact, to have better data science. Unfortunately, our field has jumped into the fray there, and there are a whole bunch of different programs and movements of various sort that are for good, that are trying to ensure that, in fact, data science is used for good, and that the technology improves and becomes, in its own way, good or responsible. And these vary from conferences and the work of centers such as yours. Oh, sorry, I don't have your logo up there. I got my own. But also whole foundations and then classes, books, and other sorts of things, all making real progress. Whoops. Okay, why are we moving by ourselves? This is very upsetting. Sorry. I think we have to go. Okay, all of these movements do good in the world, and they're great things. And we work closely with several of them and have partnerships with a variety of schools and other groups. And they do great things. Some of it's, not that headline worthy stuff that we were talking about, but just little projects that make a really big difference. And so I was going to start by maybe just telling you about, okay, I think I figured out what's going on. Sorry, folks. So I tell you about one project that I've really liked. I call it Save the Birds. And this is a group of ornithologists at Cornell who have been collaborating with a couple of our faculty to try and better understand what's happening with migratory birds in the US. And they have discovered that, in fact, there are huge pools of weather radar images, and you can use that data, 20 years worth of data, which has been capturing not only storms and other atmospheric phenomenon, but of course, if you can find raindrops, you can also find flying animals. And that might be bugs, or it might be bats, or it might be birds. But with the proper analysis, you can figure out what it is, and you can start to learn about migration patterns and the populations at each stopover, and how the population of insects is evolving, and whether there's enough food, therefore, for the birds. And all of this is important, of course, to understanding long-term population health and trends related to changes in climate and habitat availability. And it's important to be able to inform policy and zoning decisions then in various areas where the birds may be stopping over. The data is a wonderful sort of find, not anticipated for this usage, but it does cause a lot of challenges, in part because of the sheer volume, 200 million archived radar files for 20 years worth. And then also because of the complexity of the analysis needed in order to get reliable biological information out of the data. So, for example, to take just one specific task that this project has undertaken, tree swallows are a class of migratory songbirds that are really important insect eaters, and they have a declining population. They're also really interesting because they congregate in large roosts at night with thousands to millions of birds in each roost. And they're so tightly packed in those roosts that when they leave in the morning, they show up on radar as a distinctive pattern of expanding rings. So understanding what has been happening to them over the past 20 years would be really significant from an ecological perspective. However, even with all this radar data and pretty sophisticated deep learning algorithms, this analysis is proven to be very challenging. Radar data are not natural images, so object detection systems and frameworks designed for natural images won't work. The radar images actually consist of some 15 channels of data, and they represent different measurements with sort of different elevation angles, and are much more complex than normal RGB images, which have the 3 channels, basically. Furthermore, it's not so easy to tell when you found a roost. What you're seeing in these top pictures are radar images, in essence, colorized a little, but radar images taken 16 minutes before dawn, 6 minutes, et cetera, 4 minutes after dawn, and so on, of a particular roost. And you can see it starts out with a huge, dense set of birds, and over time it expands outwards. But if, for example, you were looking at a single image, like this one, it's hard to know whether you're looking at the remainder of a roost which took off, or whether it's noise or debris being blown around by winds, or who knows what all else. So understanding the behavior of the roosts over many frames is critical for detection and for answering biological questions. So as a result of these challenges, Professors Maggi and Dan Sheldon at UMass found a solution where they combine multiple different models and a feedback loop, and do proper data science, right? To try and figure out what's going on. In particular, what they ended up doing was building a single frame roost detector, which is based on an established object detection framework for natural images, modified it to learn a custom mapping to compress the 15 radar channels down to 3 RGB channels, and then built a tracking system that assembles the roosts into sequences across time, trains linear models to rescore the initial roost detections, and then recreates the sequences so that the result cleanly leverages temporal information about the roost sequence. They used this system way back in about 6 years ago or so to look at roosts across the entire eastern US on a daily basis. And they did it for an entire season, for fall through winter, as the birds were in motion. And we're able to get about 67% precision in identifying these tree swallow roosts, with most of the misidentification coming largely from precipitation, wind farms, and the roosts of other birds, because other birds also roost. They just don't usually do it in quite the same scale. So this has been really interesting and useful for science, for ornithology, but also has had implications and enabled some of the areas where development was proposed and so on, to make better decisions about how to move forward. So that's just an example of data science that's doing good. It's a small example. It's one study. I'm sure every single one of you has participated in something that has done something really similar to that and had a good impact on the world. But at UMass, we kind of want to do more. And so we have a vision for our college that we call computing for the common good. And by computing, I embrace algorithms, analyses, systems building, just sort of all the aspects, that just sort of lumping them together and calling them computing. So per our vision, this is really about being excellent in research and education to enhance well-being for all. And I think, again, many schools have similar ideas, but our research goals include not just computing being used for good, but good computing. And I'll say a little bit more about that in a minute. Trying to make computing that is less prone to cause issues. Then we also have a set of educational goals. We're very focused on trying to provide our students with the knowledge and skills they need, not only to pursue rewarding careers, and our graduates go on to do great things, and we're very proud of them, but also to do good as part of that in a rapidly changing world. And finally, of course, we like to live our values. And so we care a lot about excellence and integrity, inclusive collaboration and impact. And we want to use our technical skills to demonstrate the value of good computing in the world. So what is good computing? Well, if you look in a dictionary, you'd find a lot of different aspects to what good is, right? Good can be pleasing, a joy to use, maybe in this context. So something that does what it's supposed to do is fun. Interactions are easy. I won't go through all of these, but it can be helpful to and assist us. It could be virtuous. It might be proficient. It's just one thing that's good is doing the right thing fast, quickly, accurately, and so on, reliably. It might protect us and keep us safe. It not only shouldn't harm us to use it, it should help us improve. And really what we want is to be able to trust it, to think of these, whether it's an analysis, it's data science based, whether it's new algorithm or a brand new system that we're rolling out, we want to be able to think of it as our partner that will help us stay well. So great, but how would we create such a thing? We don't know. That's the short answer. Sorry. But we do think that you can start to think about principles that might be involved, and that those may lead you to areas of research and places to focus, and that over time, we will learn to do this better and better. And so here I'm proposing 4 principles. I don't think they are sufficient conditions by any stretch of the imagination, but I do think if you wanted to call something a really good system, they'd all be necessary. So good computing, it's got to be well behaved and robust. It's got to hold up. It should be explainable. It should embed some of the key values that we just talked about, some of those things we care about. And it should augment us. It should be helpful. It should enable us to do more than we can do today or to do it better. So what I want to do in the rest of the talk is just sort of illustrate those. And I will do so just by pulling on a project, an interesting, at least to me, project that illustrates what people are doing to advance the state of the art in one of these principles, and gives a feel that way for some of the research that's going on through our Center for Data Science. And so I will do that, and then I'll talk very briefly about some of our educational undertakings and goals and some of our service activities, including our very obviously well-named for this talk, Data Science for the Common Good, and chat a little bit about what that does. So first of all, this whole area of should work and be robust. At its root, frankly, computing for the common good is going to build on the work that's been done in computer science since its infancy, because if you don't have systems that work correctly and that work in well-behaved sort of ways, you can't possibly trust them. It can't possibly be good. So challenges such as program verification, highly available systems, theoretical foundations of algorithmic complexity, security, advances in these areas, among others, will be critical to achieving good systems. And these will also require a more integrative approach. That is, today, often we might look at correctness on one side, or performance on one side, and robustness on another, and so on. But really, what we're finding is that over time, we have to look at really, how do we optimize across a whole range of properties that we want to achieve. And so that will certainly be one area of research, probably for most of the combinations of characteristics that you would want. We need our systems to be secure, also perform, We need them to be verifiable, available, and so on. And then the other things that becomes very critical today is that we are putting systems and we're doing analyses in very complex situations. And so there is not, we're not at a point where any system we design will ever be able to work in all cases or circumstances. So we need to sort of design systems to know what their limits are, and take appropriate action as they get past those limits. We also need them to be able to adapt to changing conditions or inputs. So one place where this comes up that's really obvious, and you might say robotics isn't data science, but actually it's all data science under the covers, if you ask me. So hope I haven't offended anybody, any roboticists in the room, but all of the analysis that we do for these sorts of autonomous vehicles is really based on analyzing a lot of data, building models of that data, offline models often, that will be used, and then often, in addition, having to fold in new data as things change. So for example, Shlomo Zilberstein, one of our faculty members, he's working with his students on how do you have rational agents that make appropriate decisions, especially when they don't have enough data, enough knowledge, or computational power that they could possibly do a full-fledged optimization of the best course of action. So he's worked with things from cars to autonomous cars to drones that are inspecting, doing plane inspections, right? And they find that what they end up doing is multiple levels of modeling and then data analysis, particularly a high level sort of area that determines the strategy, optimizes the amount of thinking time that the agent has to do. So an example there would be having the autonomous vehicle choose a route to its destination or deciding which area of a plane to inspect. But then there has to be an operational planning level that produces the detailed plan and allows the robot to react to changing conditions, avoiding a pedestrian, or maybe spotting a possible defect and changing the motion planned for the drone. So there's a lot of progress that's been made in this field, and obviously we are all of us familiar with some of what has to be done in this area, just from using our apps and so on today to navigate us around. It's a little more complicated, of course, when you're dealing with a whole vehicle without a human being inside. But there's still a lot of work to be done on the whole planning front. Today, most systems plan for each individual task they have to do. If you have a new task or you repeat a task frequently, you still go off and do a new plan. And so that's true even of your mapping software. Today, you tell it one destination, and the next time you tell it, it figures it out all over again. This, however, is slow. It can be computationally wasteful. And so researchers are developing mechanisms to apply existing plans to new situations. Faculty and students at UMass Amherst are trying to take these efforts to a new level, in which you can kind of figure out what similar planning problems are likely to be encountered. And then if you know that that's likely to happen, why can't you directly search for plans that will work across a large class of similar problems? So it's another way to, it's another place to optimize in some sense, to reduce the amount of future work you'll have to do if things change. And it feeds back into this notion of strategy versus operational planning, because if you had a parameterized or a more general adaptable plan that you took for your strategic plan, it makes it much easier and faster to adapt as changes come in. So that's some of the work that they're doing in the space that I think will turn out to be very important as we go forward to making systems that can adapt to change, be more robust in that respect. There we go. So explainability, another area that is on everybody's minds. And DARPA, of course, has their explainable AI project, has had for a while now. It's still the case that that it's going to be a while before we know how to build systems that really embed our values and can be proven to do their jobs with integrity. In the meantime, our systems are becoming more and more capable and apparently intelligent. We have complex algorithms that are based on machine learning, including deep learning, that seem to do the right thing until suddenly they don't. Sometimes the mistakes are just funny. Why did a machine vision system recognize static as a school bus? But in the wrong context, such mistakes can lead to a self-driving car slamming on its brakes and causing an accident. Other mistakes are much subtler, leading to patterns of discrimination, for example, in medical treatment that may not be detected for years. When humans err, we demand an explanation. One of the first things then that we have to do to make our systems more trustworthy is to give them the ability to explain themselves. And that's what DARPA's Explainable AI program has been about. In that program, in our work on that challenge, Professor David Jensen and his students are creating a suite of new machine learning techniques that can produce more explainable models while maintaining a high level of learning performance. In essence, what they're trying to do is take a particular algorithm with whatever level of accuracy and so on that it has and move it to the right, that is, make it more explainable while maintaining the prediction accuracy. So the way they're working towards this is they take the learned output of these techniques, they train a causal model, they use causality as the language of explanation. It helps them to explain machine learning conclusions and algorithms in terms that are cognitively congruent with human explanations. In this process, they use probabilistic programs to model complex machine learning operations, providing the expressiveness and inference capabilities needed to explain causality. They are working on advanced causal model learning methods using sophisticated experimental design. Once an explainable model is produced, a user can query it through an explanation interface. And that interface is based on computational narrative-based organization of explanations to enable communication of temporal, spatial, or intentional elements of explanation in a way that humans can actually interpret. That whole explanation interface is actually informed by current psychological theories of explanation and by user observation to maximize system understandability through enhanced observability and directability of machine learning based tools. So that's explainability. But what about key values, right? How can we teach our systems and algorithms those values? What values do we want all systems to have, or will we pick and choose depending on where this analysis is going to be used, for example. Today, this task seems pretty overwhelming. There are too many things that we have to worry about. As a result, frankly, most of the algorithms and analyses that get done really ignore values. But what if we could agree on a small set of core values and build them into our systems? For each value, we would have to agree on what it means, both in theory and in practice. And that would give us the ability to observe, test for, and enforce these values in our systems. We're probably closest to this with privacy today. We've done a lot of work codifying what privacy means and in differential privacy, making it very concrete what that means, and being able, therefore, to actually make claims about how much privacy we can deliver and so on. But another area that has been of a great deal of interest is fairness, right? That's another value that we all care about. And so a lot of work recently has been getting done. There have been various mathematical formulations of what fairness means. But from our perspective at UMass, we have thought about it as, okay, in the simplest of worlds, what we really want is that sensitive inputs, whatever we decide that sensitive element is, should not affect the behavior of our software. So if you have a loan application and you have a picture of a guy who's green, there's a green background in the picture, and that guy's loan is approved, and then you swap it out for a guy who in every other way is identical to the first guy, but his background on his picture is purple. You'd like to know that he's going to be approved too, at least if background color of picture is your sensitive input. So that's kind of a silly example, but obviously substitute, gender, race, etc. Two people who are, kind of identical except for one of these different inputs should get the same output from whatever system. So what two of our faculty, Yuri Brun and Alexandra Milieu, have been working on is a new definition of discrimination then based on, again, causality. And they say in brief that software will be causally fair with respect to input feature X, if for all inputs, just varying the value of X does not change the output. And they've built a system then that can use that definition to actually test any system or program that's out there. So and it can test it with respect to a particular data set. So you can actually answer questions such as, how much does my software discriminate with respect to input value X? Does it discriminate more than 10% of the time, and against what? That software test suite generator is available out on GitHub, and it has been used to evaluate fairness of 20 real software systems that claim to be fair. And what they discovered was that none of them was perfectly fair. That in fact, there were circumstances for each. Some were better than others, but there are circumstances for each that made them work better or less well. So that's an example of how we might approach taking other characteristics or values that we'd like our systems to have and embedding them, figuring out how to formulate them, and then hopefully not just changing algorithms and ideas, but figuring out how to test for and guarantee the presence of such a value. So last but not least was this principle of augmentation. There's very clear applications in this space in terms of improving human health. We'd all like to live longer, healthier lives, but frankly, often our own behavior gets in our way. Could computing help us behave better? And in this case, computing really equals data science, right? Smoke less, maybe exercise more, eat less, sleep more. These are all things that perhaps we could monitor and react to. There's a proliferation of sensors out there that are providing constant streams of data on what people are doing, and companies and researchers are definitely trying to find ways to use that data to improve lives. We are all familiar with the watch that prompts you to move around. I don't know if you can still see me, but that's my watch. That's always telling me at the wrong moment when to move. And so that's an example of a not very smart watch. So each type of behavior has its own signals, though, that have to be detected, and its own interventions that might be appropriate. For the watch, it's detecting lack of movement and over a certain time period. And the intervention is usually to buzz you so that you get reminded to move. But what about more complex behaviors like smoking? How can machine learning help us detect when a person is smoking, predict from those observations when they are likely to smoke, and intervene to help them resist, maybe distract them in some way? Can we fight obesity by learning when a person is likely to want to eat again, and again intervene to suggest a more positive activity? Some of the devices you're seeing at the bottom of the screen have been put in practice. For example, the glasses detect fatigue, hopefully before you crash into a tree in a car, crash into your computer and fall asleep, and can then trigger signals that can help wake you up and keep you awake. So this is fairly complicated data science in the sense that it's all time series, right? Lots of time series, but it's not single points in a time series that have to be analyzed. This is usually fairly rich sets of sensor signals that have to be often aligned because they're coming from different sensors or from different, really from different sensors, even if it's on a single device. So that's something that Deepak Ganesan and Ben Marlin have been working on over the last few years. They're now, we just announced Monday, they just received a really nice NIH Center grant that will form a center on using AI to ameliorate conditions having to do with aging and Alzheimer's. But a lot of the same sort of techniques that they've been developing, they expect to come into play there. Okay, that was sort of a whirlwind tour of a little bit of the kinds of data science research that we're doing at UMass Amherst, and how we're trying to advance some of these principles. We also trying to make sure that the students we send into the world are correctly prepared to understand and to think about when issues might arise. And so we do that in a variety of ways. We have first-year seminars for our undergraduates. They get exposed right at the beginning. We have graduate level course that comes back to them. They also get a fair amount of responsible computing sort of situations, ethical issues in tech through their junior year writing course, which we also are responsible for. We have a new project that we're very excited about that's been building almost role-playing games. We call it an ethics simulator. But the idea is that any faculty member will be able to customize their for their course. They might be able to come up with a custom scenario, and then this simulator will be able to run it, and students will be able to kind of walk through the sort of real life, or maybe simplified life situation that they might encounter in the real world, and usually something pertinent to that course. We just heard a wonderful talk from a researcher at Brown University about, for example, how even choosing a data structure can have long-range impacts on how fair and unbiased your system is. And so things like that you could start to simulate through this route. And then the students do a fair amount to help each other in this space. We have a peer mentorship program. We have some student-initiated experiences that put our values into practice. The students, for example, started Build, which is it's a freebie pro bono development for not-for-profits. So they go out and donate their time and energy in the world. They also started the ill-named COST. It's really a community outreach in science and tech. And that they go into classrooms and teach there. But I thought I would talk for a minute about Hacker 413, which is one of their activities that we're very proud of, that has really been the first in all of Western Massachusetts hackathon, particularly for women and non-binary. For many students, it's become very well known now, I think, as a place where you don't really have to know anything about science and tech, as long as you don't mind exploring and working in teams. You can take classes, you can learn a lot about computing, and you can they are really encouraged to build things that will help to make the world a better place, whether it's in the small, helping biology researchers find with a tool that they need to help with their analyses, to larger things that might, someday go on to change the world. So we're really proud of our students for getting that started. I also mentioned service, of course. Good example there might be our NSF Cyber Corps Scholarships for Service. So this is an idea that students come in, and they can be funded by NSF for up to 2 years. I'll say that slowly, and then they work for a federal agency upon graduation for a couple of years. We're trying to get a similar program started for the state of Massachusetts. We've been working with some Massachusetts government folks, because there are just a lot of public agencies that are really hurting for cybersecurity talent. The pictures on the side here are pictures from our Massenburg Summer STEM Institute, which targets rising 10th graders from, I would call them disadvantaged high schools, schools where there just isn't that richness in science and technology. We find kids who are interested in science and technology, and we bring them in for a 1 to 2 week on-campus experience where they get a smattering of STEM things through hands-on workshops, and they walk away feeling like they have learned a lot, and like they have seen people like them succeed in STEM, because we surround them with role models, and some of our own students, some of our own faculty, and so on, that look like them. And it's just a very nice way to kind of put some of our values into practice. But of course, the one I want to talk about here is really Data Science for the Common Good. This is a program we run every summer for our master's students. We pay our teams of master's students with a not-for-profit, could be typically an agency of some sort. So you see the Charles River Water Association or Water Authority, I forget, the YMCA, Springfield Public Schools. So we've worked with the Department of Public Health. We've worked with a whole bunch of agencies. This one, they are working with TNC. Always get confused with the acronym, but they have been trying. Oh, actually, no, I'm lying. That's the group that was working with the Charles River Water Association. They were doing studies, data collection, and then analyses of Charles River water to understand what happens to it when they have dangerous blooms and so on. But there have been a number of really nice projects with the Springfield Public Schools. They did some analysis to look at what courses were good predictors of success for our students. So I think with all of that, I've given you kind of a view of our vision about computing for the common good. As you can see, in our vision, research is going to produce better data science that's going to better reflect our values. Education will pass on our values, and service will exemplify our values. But despite all the different things I talked about today, there's clearly a lot more to do to get us really to computing or data science or whatever for the common good as we envision it, trying to make this more robust, good vision of computing. In particular, there has to be more work on what are the principles, and my sort of half-dash guess on here, some of these are okay, is nice, but what really would characterize good computing? How can you put that on a solid theoretical foundation? What are the tools that you could put in place to help, and so on? But then we have to go beyond that, right? We have to think about how to ensure that these systems are meeting our criteria, maybe through testing, maybe through verification techniques. Quality also has to come to mean more than correctness and efficiency. It has to somehow check for goodness as well. So what does that mean? Lots of interesting pieces of work that you can think of in that space. And since any technology or analysis, for that matter, can be abused, we can also focus on education and policies and perhaps even laws that would provide disincentives for bad behavior and incentives for good. We know that there are many groups that are already working towards these latter goals. ACM, IEEE, the American Statistical Association, and the data science study that I did. Well, all of those groups have created professional codes of conduct for their members, but the study that I led for the national academies, or co-led more accurately, took that sort of a step further, thinking that, those are very nice, but we need to teach them to our students. We might even need like our own version of the Hippocratic Oath that doctors take before they begin their practice. So several schools, such as our own, are now requiring students to take a course on ethics as applied to or relevant to computer scientists or data scientists in your case, right? We need standardized and compelling curricula for such courses. And our legal systems and systems of government can do a lot to promote both the research and education needed, as well as the further use of good technology and technology for good. So I'll end on a commercial. We're hiring, so if you have graduating students who would really like to join a great community as postdocs or faculty, send them our way. Always looking for PhD students as well. Very happy to have you join us in that literal sense, but also I would say join us in the crusade. Let's try and really figure out how to make data science that lives up to these high principles and ideals. And I will stop there.
Laura, thank you so much. Your talk was fantastic at, giving us a deep overview of data science for the common good and looking at all of these issues. There were some comments in the chat, and there's a statement I'll read from one of the attendees and then ask for questions. I have some I'd like to ask, but if anyone on the Zoom would like to ask a question, please just put it in the chat. So one of our attendees commented that it strikes me that, especially for explainability and fairness tests, if one can measure how well good computing is doing, that adversarial training can produce models that, quote, look explainable or fair, yet are deeply flawed and favor some other hidden agendas. Hence, this seems like a somewhat hopeless task. Profits and self-interest will always trump altruistic application design. Your thoughts?
I can't be that pessimistic. I'll quote whichever philosopher. No, that's bad. But you know, the arc of justice toward the arc of the world trends towards justice. I think you are correct that there will always be somebody who will find a loophole. But I also know that every time people find these aggressive ways to break things, there are people who find ways to bar the doors and react. If you're saying that, yes, we will be in and that we will never quite get where I'm saying we ought to go, I know that. I agree with that. I think if we don't try, though, shame on us. That would be my answer.
So in your talk, you mentioned a real diverse variety of data sources, from radar imagery to time series data, for instance, the health fitness data and so on. Do you have any thoughts on storage systems and databases and how we're going to deal with this ever increasing variety of data?
My favorite. You know, I made my career out of dealing with a wide variety of data, and I used to tell my kids that you know, every few years they'd ask me, "What are you doing, Mom?" And I'd say, "Well, I'm working on integrating diverse kinds of data," because it was true. And finally, one day, "Weren't you doing that like last year?" Last time I asked, and I'm like, yeah, because it's full employment. That's another one of those tasks. We'll never have the right answer, but I think there's some, you know, I'm not here to say that I don't know of the technology that I think will rule them all. I'm out of the game of advocating for my particular technology. I have to admit that people ask me a lot about federating different sources and systems, which is sort of how I got deeply into that game. And I've been asked to talk people out of using federated approaches, and I can do a really good job of that. It's not a silver bullet. It's a great prototyping tool, the way we built it. And as a result, what happens is there are these big ideas that keep coming around. The technology moves forward, and then you apply distributed to it, and then you apply federation to it, and then you apply, you know, this technique and so on, and we advance. And then somebody comes up with a better storage technology, and then we kind of do it again. If you watch the pattern, so I think there are some very important tools that we'll never get away from. Nobody's going to build the one giant storage case for diverse data in the sky, right? I mean, the cloud is there, but it's not all unified and accessible there. But we will again, I guess maybe that's where my belief in principles comes from. There are some things that you will always do. You will use distribution. You will have different ways of caching and pre-caching things. You will, I mean, you'll just apply them in a new setting, and there'll be lots of research and innovation, and it'll be cool, and we'll get way further, because believe me, you can store a lot more heterogeneous data today than you could when I started my career. These gray hairs will attest.
So early in your talk, you had these fantastic headlines about the great things that computing and data science were doing for society, but then also all of these scary things as well. And we hope that explainable AI and fairness, et cetera, will help build these better systems for good, rather than these horrible nightmare outcomes. How do you build trust with the general public for this type of research, or more importantly, these types of systems that get deployed?
So I'm really glad you asked that. So I am in the process of launching a sort of a new, at least a program for UMass, in what we call public interest. We don't call it, the public calls it public interest technology, right? So that's become a new academic buzzword. But as we're thinking about our programming in this space, there's a big piece about educating students. There's also a big piece about cross-disciplinary research. But really the third leg of the stool has to be public outreach and educating the public, because for too long we've left it to the internet. The press is actually good people, despite those headlines. I mean, most of the time they try to get their facts straight, but you know, it's just stuff that's out there, and we think that we can do a lot more through outreach into schools, into communities, and so on, to work with that. We're hoping to leverage our campus in Newton, Mass. So it's called Mount Ida campus. It was a college that UMass bought a few years back, and it has the advantage of being, 10 minutes on a good day by subway to downtown Boston. And so we're hoping to use that as a convening place and a venue for people to discuss these sorts of issues, and to take them out into the larger metropolitan world that we can access through that. So it is an educational task, and that also is insoluble before my friend says otherwise. I know that, but again, I just feel you have to try.
Okay, so let me just say, are there any final questions? Well, thank you again, Laura, for the fantastic talk, and thank you to our audience, those here on Zoom and those on YouTube. So thank you again.
Yeah, my pleasure. Thank you.